Hello and welcome back. In this session we're going to talk about the set difference or subtraction of sets. We saw when we discussed inverse and identity elements that although we had identities, we did not have inverse elements for our basic set, our basic binary set operations. So we did not have an additive inverse. Now in real numbers, we can subtract numbers by adding the additive inverse of another number. So we cannot do that with sets. We saw we couldn't reduce the cardinality of any set with a union of anything. The union operation could not have the effect of reducing the number of elements or the cardinality of a set. We can, however, do that with the intersection. So we'll see that although we cannot add an additive inverse to subtract elements from a set, we can multiply with the complement of or the negative in order to subtract elements from that set. And we'll see that in the next few slides. Now let's officially define the set difference. First we review the complement of a set. The complement of a set A is the set of elements x given that x is an element of the universal set and x is not in A. So it's all the elements in S that are not elements of A. This is also called the absolute complement. We have just learned of it as a complement. We'll now specifically call it the absolute complement. Now, with that in mind, we can define the relative complement or the set difference. So the relative complement is the set difference, and it's written for two sets B and A. It's written B minus A, also written B backslash A, and per definition, the set difference B minus A is all the elements in the set B that are not elements of A. And this equals the intersection of B with the complement of A. Now first, if B happens to be the universal set S, then the complement equals the absolute complement. Then the relative complement ends up being equal to the absolute complement. Let's try it out. We'll substitute B with S. We get S minus A equals S intersection the complement of A. But we know that S, or our universal set, is the multiplicative or the intersection identity element. So the intersection of the superset with any set just equals that set back. So S intersection AC is just AC. So we have back S minus A equals AC. So that shows that if B is our universal set, then our relative and absolute complements are equal. Now, it follows that for any set, B minus A equals the intersection of B with the complement of A. Remember, because all the elements the complement of A are all the elements in the superset that are not in A, so it's sort of the negative image of A. And the intersection of that with B are the common elements. So we get the intersection of the negative image, if you will, of A with the set B. And we'll see how this works a little bit more visually in the next slide. So let's take a closer look at the set difference, and we again have B minus A, and we can see from some Venn diagrams I've made here with a set of 2D positions, we can see that B minus A equals the intersection of B with the complement of A. Now first, I've made Venn diagrams with a set of 25 positions, a 5 by 5 set of squares, where if a particular element is in the universal set, but it's not in our set of interest, then the square is empty or white, and otherwise it's blue. So our set B is the top left of the images, and our set A is the third one on the top row, and the difference B minus A is the bottom image. Now remember, the difference, B minus A, are all the elements in B that are not in A. And the complement of A are all the elements in the universal set, or all possible elements that are not in A. So if we take the common elements of B with all the possible elements in the superset that are not in A, then we get our set difference. So what we've done is, instead of adding the additive inverse, which would be the negative element, if like we would do in real numbers, we cannot do that here. Instead of that, what we've done is multiply by the complement, or we intersected with the essentially the negative in order to get the set difference here. Now let's recap a bit here. We've already discussed most of this, but I will summarize it here, and we will add also the difference of Boolean variables here. Now, if we're talking about real numbers, for numbers A and B in the set of real numbers, we can subtract A from B, so B minus A, by adding the additive inverse of A to B. So we can turn the difference into addition and negation. So B minus A is B plus negative of A. Now with sets we couldn't do that because there is no additive inverse. We don't have an additive, we don't really have a negative element, which would be the additive inverse here. We saw that the union can only serve to either leave the set unchanged or increase its cardinality. So in order to subtract, we found, and we saw in the previous slides, that we must instead multiply by the complement of A, or we do the intersection essentially with the negative of A rather than the union. So with sets, B minus A is B times the complement of A. Now with Booleans we have a very similar situation to sets. Adding a Boolean is the OR operation, and we had no additive inverse there either. What we can do is do the AND operation, or Boolean multiplication, with the logical complement. Logical complement being not A. So B minus A for Boolean variables is B and not A. Not A being the logical complement. Just think about it. If B is 1 and A is 0, so we're subtracting 0, then we doing not A in this case is 1, and B and 1 remains B. So that works out. So B minus A, if A equals 0, ends up being B. Now if A were 1 and B is still 1, then not A is 0 and B and 0 equals 0. So we've shown here effectively that this is subtraction for Booleans. Very similar to the set concept. Now let's do a couple of examples before we summarize the session. We'll start with a few complements in the top row, and avoid looking at the answers for a moment. They are listed here, but let's just look at the top row. So if we take the complement of a set A, what do we get? So we're essentially taking sort of the negative image of the negative image, and we just end up with the set A again. Now what's the complement of the empty set? Remember, by definition, these are all the elements of that are in the universal set that are not in the empty set, and the empty set has nothing in it. Therefore, the complement of the empty set is the universal set. Now, what is the union of A with its complement, the set A with its complement? So now we have all the elements that are either in the left operand A or the right operand, the complement of A, and we again end up with the universal set. Now let's look at a couple of set differences, or actually we should just say differences in the center row. First we have S minus, in parentheses, S minus B, and these are sets. Now remember that we define the absolute complement of B as the difference between B and the universal set. So S minus B, by definition that we saw earlier, is the absolute complement of B. So what we really have here is S minus BC. And now we can use our intersection definition. So S minus BC is actually S times the complement of BC. And we saw, just like with the complement of AC, we get A. So the complement of BC is B again. So we end up with the intersection of the universal set with B, which is just B. Now the middle difference here is a bit of a tricky one because we're not dealing with sets. These are real numbers. We don't have brackets, so the difference is just 7. 8 minus 1, real numbers, is 7. Now the third one, I have written the number 8 in a set, and we're subtracting the set with the number 1 in it. There are no common elements. Now we are dealing with sets, so the set with the number 8, and we're subtracting the set with the number 1. And by our definition of the difference, these are all the elements in the first set that do not contain elements in the set that we're subtracting. So we just end up with the set with the number 8 again, because the set with the number 1, that element 1 is not included in our first set. So this subtraction has no effect at all. So that summarizes, or that actually reviews just a little bit. We'll have more review on these materials later. We'll get ready to summarize this session next. Let's summarize really quickly. We covered here the relative complement of sets, which is also called the set difference, and we showed how this is different from the difference of, say, real numbers, where we could simply add the additive inverse of another number. Here we are effectively multiplying the complement, and we saw that this is also the case for logicals.